Hello guys, what's up? How are you guys doing? Uh, as requested, we are going to start with PCA and LDA hands-on. So the data set that I've chosen for this exercise is a very popular one. If you look at my screen, it is handwritten digits, which you have to recognize whether it is a 5, it is a 2, it is a 3, basis the pixels. So if I talk about the data set, if I talk about the data set, this is how it's going to look like. I will show you in when we are going through it. This data is first of all available in Sklearn. This data is available in Sklearn, and these are some of its traits. Okay, some important information. So the data set contains images of handwritten digits. Okay, 10 classes where each class refers to a digit. So you have 0 to 9. You have 10 classes. It is a multi-classification problem. How many instances? Mean these are the number of rows. These are the number of columns. Y64, it is an 8 by 8 image. So the pixels are populated in 8 by 8 matrix. Okay. There are no missing values. So we are going to look at how PCA and LDA can be used to reduce the dimensions, and if time permits, or in part 2 we will look at end to end using the same data set, how you can first reduce your dimensions and then build a classifier on top of it to do the predictions. Okay, for this session, for this video, we are only going to restrict and understand what PCA and LDA are. Okay, and how they can be useful in reducing the dimensions. Cool. All right. Without a further ado, let's start. Let me add in a few cells here. Perfect. So the first thing that I want to do is I want to load in all the libraries that I want. So importing the library sort packages, and I want um speaking by MP, and then we'll also matplotlib plot as PLT. And let's also, for our visualization, also let's call in the seaborn. Okay, so this is how we load in the libraries, and then let me show you how will you load and read the digits from the sklearn data sets. Okay, so what you need to do is yeah, it is showing us. So from sklearn.datasets, import load digits. So if you go and search for load digits and slash sklearn, you'll reach a point where you can see what that data set is. Actually, it is this information is also coming from there. So let's load in the data, and let me show you how will this look like. Let me first leave this in, and by that time, let me design my X and Y also. So digits dot data, that is this, and I want my Y to be the target variable as well. Digits dot get, and let's see. So what is this saying? Digits dot data X dot. Okay, so this is how this it has 1797 rows and 64 columns, independent features, which is 8 by 8 pixel. And what is your target variable? Target variable is nothing but for each row, you have the digit. You have the digit. Let me show you. Let me show you how will this look like. Okay, come in here and let's plot the data. Plotting the data for view. Okay, for our view purpose. So for this, what I'm going to use is I am going to use PLT, but here what I need to do is I need to set my color map, and I want it to be only binary so that we get only black and white images. Once you set that, then what we can do is for IM range. So what I'm going to do is I'm going to show you 10 columns and 10 rows. That is what these loops are going to be. So each space will be a subplot, and each subplot we will portray or show the digit. Okay, so that is why the range is for I, range is this, and no, I want for J in range again 10, and then for each of this I want AX to be PLT dot subplot. So what I need to do is I need to bring in this subplot. Let me see if this is right. I plus 10, J plus 1. Okay. I am show this equal to, so this needs to change. Let me make this as x dot axis is equals to. So why I am off switching this off, I will show you. Because for each image, no, it will show some values. It will show the axis, the y-axis and the x-axis. So to avoid that, what we are going to do is we are going to switch it off, digits dot images, and in images I want I into I into 10 plus j plus j is what I have here. See, and then after you come out of the loop, and then okay. So this is what has happened. This outer loop is giving me the columns, and this inner loop is giving me the rows. Okay. So 10 by 10, what I have done is I have for each subplot, this is one subplot. This is one, second, third, and so on. I have printed the image. I have printed the image. So basically, that is what you can look at the code, pause it, look at the code right at your end as well. But ultimately, what we've done is we have plotted each of the digits here. So how many rows are we looking at? 10 cross 10, 100 rows. 100 data points we have plotted here. So here you can see it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so on. And then you see, these are changing. Since they are 8 by 8, they're not pretty clear. They're not very clear. And also since we are contracting them, it's coming like this. Okay, cool, cool. All right, let's move ahead. Now, what we want to do next, we want to, from Sklearn, we want to apply principal component analysis, then principal component analysis. Okay. So for principal component analysis, we have to import, we have to import principal component analysis. So we are going to import it from the decomposition. From decomposition, we will import the PCA. I will show you from Sklearn dot decomposition import PCA. Okay. And then PCA is what I want. And then from also from Sklearn, we will also standardize this. So I also want to, um, import the standard scalar. Okay. We are going to import the standard scalar next, coming next. Now the next point is that we need to scale. We need to scale our data points. Okay. Scale the, scale the X. So how you're going to do that? You're going to instantiate a standard scalar object. Standard scalar object. And then what you're going to do is you're going to say X standardized equals to scalar scalar dot fit transform your X. Okay, so whatever you have scaled is now going to be in this X standard. Okay, X standardized. Let's run this. Why I'm doing it is so that everything is in on the same scale. You can skip this because this is in pixels. You can skip this as well, but it is always a good practice to do it. Okay, cool. All right. Now the next step is fit the PCA. Now this is where I'm going to show you different things about PCA. Okay. Now what I'm doing here is I am not passing any parameter here. I'm not passing any parameter here. Let me show you sklearn PCA also here. So if you open up the documentation, okay, you see there are different things. So n components means none. Here, how many components you want from principal component analysis? You can pass that here. Okay. So for now, what I'm doing is I am not passing anything. Why is that? Now you see it will show you that this has been fitted and you have a PCA kind of a model there. Why? Because I want to show you this PCA dot. It will give you what? It will give you those eigenvectors. It will give you the principal components, right? If you do PCA dot explained variance ratio, this function, let me round this to 3 also. This function will tell you all the principal components. Will give you all the principal components that PCA has fitted and has found out to be important. Okay. So here is your different dimensions. All these principal components are on different dimensions. What is this? This is PC1. This is the first principal component. This is the second one, third one, fourth, fifth, and so on, and so on. And also notice one thing, PC1 is the maximum principal component. Remember, I told you that this is going to be the maximum one. Maximum variance is being explained by this PC1. And how much is that? With this number, you can say it is 12%. This is explaining another 9.6%. This is explaining another 8.4%, and so on. And see the ones in the end. They're literally explaining very little information, right? Right? Less than 1%. Cool. So this is what you have received as principal components. And if you check, you will see 64 of them. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. 7 and 9, 63 and 1, 64. So you had 64 columns to begin with. Now you have principal components equal to 64. Now while you're working on dimensionality reduction, you need to choose your principal components, your D dash, in such a way that it is lower than your D. Agree with me? Agree with me? It should be in such a manner that D dash should be less than D, where D dash are your dimensions after applying PCA and reducing the dimensions, such that it is less than D. Let's try to do that. Let's try to do that. Now there are again two ways. I told you that we can also get the number of components that we want to. Let me show you that first. Let me show you that first. So PCA fitting with two principal components. What you can do here is, rather than fitting there like this without any parameter here, you can fit it with passing this parameter n components equals to 2. Look at this. Number of components to keep. So what I'm saying here is, I want only two components here. I want only two components here. Okay, let's run this. Let's run this. And here what we are doing is, we have PCA and components equals to 2, and we are fitting it on our standardized. Let's run this. So now you've got PCA on two components. Now if you see PCA dot explained variance ratio, see, now you have only two. You have only two because you have chosen it to be only two components. So rather than showing you for all, it is showing you only for the first two that you have chosen. And they are, how are they selected? First two, which are going to explain the maximum variance. Okay. So how much are they explaining? This is 12% and this is 9.5%. So around 21.5% is being explained. Okay. Cool. Cool. All right. All right. Let's also now you know how you're going to do this, how you're going to fit this. Let's also now look at X embedded. X embedded, I'm going to say, is nothing but my PCA dot, here I am going to say my PCA dot fit transform on X standard. Why I'm doing this is because I have already created this instance. Let me do that here again. PCA length equals to 3. This time let's choose 3. Okay, let's choose 3 for the time being. And now what I'm doing is, I am now fitting and transforming and saving this as X embedded. Now because all my 64 are now going to be shrunk to 3, right? So I want to use this. I want to use this going forward for my predictions. That is why I am saving it as a separate entity, and that's how you can save it. This will be even more clear when we go to the part 2, where we will apply it for classification of these digits. But for now, that's how you will apply it. Okay, that's how you're going to apply it. And let me show you the X embedded dot shape. See, you had how many X to start with? You had 1757, 97, right? And 64 columns. Is it making change on any number of rows? No, right? You still have the same number of rows, but the columns have changed. Why? Because you have said, I want 3 columns, 3, not columns, 3 principal components. Three principal components. And how much of a variance are you capturing with three? This 12, 9.6, and 8.4%. How much will this become? 8.4 plus this is going to be 10, 18, 18, 20, 30%. Close to 30% you're capturing with three principal components. Okay, cool. All right, all right. Coming to the next point. Coming to the next point. Now, here, let me show you. First, let me show you. Now, these X embedded, I told you that the principal components are not having the same meaning as pixels or your original columns. How? Let me show you. Look at this. This has no meaning now. You cannot say this is the value of pixels. No. It is in a different dimension, and the data points have been projected on that component. So it has lost its meaning. Now let me show you, and let's plot all the digits based on X embedded. Okay. Now whatever I have reduced the dimensions, I have saved it in embedded, right? Let us now plot this to show you that, I want to do a comparison between LDA and PCA in visualization to say that PCA is probably not as good as LDA when you talk about the visualization aspect. Okay. Let me show you. Let me show you. How is that? So here again, ELT dot set color map. Now I'm going to do a 10 colors because we want to show the clusters, or all the 10 different digits. Wait, access is nothing but dot. Here I want to save as scatter X embedded. I'm going to take all the rows and the first column or the 0th column, comma, X underscore embedded, and again all the rows and the second column with index 1, and then the color I want is based on digits dot target. Okay, it is going to give you the digits, the color based on the target, whether it is 0, 1, 2, and so on till 9. Okay, all right. Let's also put in the legend so that this is clear. Legend. Ax dot legend. Scatter legend elements. Title is classes, or title is digits, and I also want it to be on the upper left. I want it to be on the upper left, and Ax dot add. I already have that. And then we are going to do plt dot show, and it is a generally good practice that you close this also. Let's see. So it's going to take some time. On your upper left, Okay. Here, what you're doing is, look at this. Now we are visualizing. We had three columns, but I'm using the first, the zeroth, and the second, which is the index 1, to plot it as a scatter plot between my x0 and x1. Okay, embedded 0 and embedded 1, basically. And we are trying to visualize this. Look at this. 64 dimensions of data you are able to visualize. But if you look at this really, really closely, right? Well, 4, which is denoted by this violet color, is okay. You can distinguish these are, all your fours together. You can also probably identify this pink, which is 6, right? Also, somewhere here, gray is also scattered. But what about the others? This blue, which is 0, is also somewhere here. It is not really a good visualization, right? Not really a good visualization. Everything is messed up here. Everything is messed up here. Why? One, because you're coming from 64 to how many? Here, 2 dimensions. You're plotting it in 2 dimensions. One is that reason. Second is principal component analysis, PCA, is not recommended for visualization. You can do it. As I told you earlier also, I would not recommend you guys to go ahead with this. PCA specifically for visualization. Okay. PCA specifically for visualization. I will not recommend you guys to go ahead with that. Okay, cool. Now the other thing that I want to talk about is fitting the PCA with or based on the variance of information capture. Now, what was the other way? What was the other way of fitting the PCA? Here, what we did was, here we said, I want three components. I want three components. So it fitted the PCA with three components and gave us three principal components. Now, I want to capture in most of your real world problems. That's not how you will use PCA. What you would want is you would want to uh, capture as much as information that you can. You are not restricted on the number of components. You want it to one be lesser than the original data set, but you also want to you also want to capture 90% or 95% of the variance of the information. Okay, so that's how you will implement. Let me show you. So here, if I say PCA equals to PCA, and instead of giving components, instead of giving a number here, if you say 0.9, it is going to give you all the components which are capturing 90% of the information. Let me show you. Let me show you here. Let's call this as X embedded. Let's call it 90. And we are going to do what? We are going to say that PCA dot fit transform on X standard. X standard was what? Your main data set. And you see the columns? How many columns does it have? 31 columns. It has 31 columns or 31 features. You're still reducing your dimension, but you're capturing 90% of the information. Let me show you. See, this is 12. This is 9.6. Here we had 30%, 36 and a half, another 5, 41, 45, 49, 52 something, 55. If you keep on adding, you will see that you are getting what? You're getting 90% of the explanation explained, information explained. Okay, how many are there? 1, 2, 3. So this was 9, right? 9 and 9, 18. 18 and 27, 27, 28, 29, 30, 31, till here. You're capturing all the principal components till here. These are the 31 of them. Okay? Clear, everyone? Cool. That's how you're going to fit your PCA. That's how you're going to fit your PCA. Okay? Cool. Now let's also look at LDA. Let's also look at LDA, Linear Discriminant Analysis. Okay? Now for LDA, we are going to use the same data set. We are going to use the same data set, but we have to now call or import LDA from sklearn dot discriminant underscore analysis, and I'm going to call it as LDA. sklearn. Okay, that is how you import your LDA. The entire thing is same. Rest everything is same. Whatever you did with PCA, you can do with LD also. It's just that the concept is different. How it works is different. So we looked at during our sessions. PCA moves with the purpose of capturing the maximum information. LDA works with the purpose of maximum separability. Maximum separability. Okay. Let's try and implement this as well. So let's fit the LDA, and here let me call it as LDA equals to LDA, and I'm going to fit it with two components. While this is running, let me also open this. Look at this. Number of components, again, the same thing. Number of components is again the same thing, right? Okay, let's look at this. See, X embedded LDA is having how many columns now? Two. Is having only two columns. Is having how many? Two columns. And how do you want to know the explainability? Same. LDA dot explained variance ratio, and let me also round this to 3 again, so that the number is not huge. You see, what is this telling you? This is telling you the components, the latent discriminant components. Two. First one is this, second one is this. If you simply run it, if you simply say LDA, okay, and without passing any, if you do X, let me say LDA, let's call it as LDA dot fit transform. And what are you going to pass? You're going to pass your original data set. And let's call this as X underscore LDA. See, one important thing for you guys to remember is that you also need to pass Y. Why you have to add Y? Because this is a supervised learning. Remember, here in PCA, when you were fitting the PCA, did you pass any Y there? No, right? You did not pass any target variable. What is Y? Look at this. Y is your target variable. You did not use this when you were fitting the PCA, but you need to use this. You need to use this when you're fitting your LDA. Why? Because this is a supervised learning. It needs to know which class na, so that it is able to maximum separate, so that it is able to maximize the separation. Okay. How many is this getting now? 9. It's getting how many? 9. It's getting 9 of them. See? Getting 9 components here. Above that, you are not getting maximum separation. This is what is giving you the maximum separation. These are the 9 components. Okay? Cool. All right. All right. I just want to make sure. So we have this. Let us now also visualize this. Same as that. Let me copy this. Let us also visualize this here and this X embedded. What do we have X embedded here in case of LDA? We have embedded LDA, embedded LDA for distinguishing. Let me run this as well. See, do you notice this is much better compared to PCA? Do you notice it is much better compared to PCA visualization? See, it is all messed up. Here, also it is messed up because LDA is also not the best algorithm for visualization. But you see, this clustering is really, really better. This visualization is much better than PCA. You're able to distinguish all this separately, this separately. Red is in this corner, green is in this corner, and so on. Okay. So there are better algorithms than PCA when your motive is to do visualization. Okay. Probably in later sessions, I will cover TSNE and UMAP, which are much better. Are especially TSNE, that algorithm is specifically made for this visualization. Okay, so in the next session or something, or in the next video, I will cover that. All right. Okay, cool. That's it. So in this video, we are going to cover only this much. And what did we see? We looked at how PC can be applied, how LD can be applied, all the ways of applying it. Basically, you can get the number of components that you want. You can also say that, okay, this is the information that I want to capture. And similarly, we also visualized it and saw that PCA is not really good for visualization, probably for maximum, information capturing, but definitely not for visualization. Okay. In the second part, we are going to cover, all right, if we apply this, how do we solve a problem next? What after this? Here we have understood how to apply it, but how do we solve it in a problem? How do we leverage this in a problem? Okay, cool. All right, that's it.